We're back. All right. Think it'd be okay to start now? Or should we wait a little bit?
I thought that he was coming.
There he is.
Hi, Professor.
Hey. All right. So I'm sure you've read about conjugate acid base pairs by now, right?
Yeah, and then we did it a bit too in like Gen Chem.
Yeah. And we know that those are a conjugate acid base pair is a pair of molecules that are different by only a proton. And I'm going to keep using the word proton and assuming everybody knows that proton means H plus, because that's all it has.
Professor, if you're
Proton
writing on
in
the
its
starboard, we can't see it.
Oh, thank you for pointing that out. All right, so here we go. Share screen. Yeah, got it now. So yeah. So before we start this problem, we have to know that a conjugate pair is a pair of molecules that are different by only a proton. And a proton in your mind, don't just think proton. Yeah, it's the same thing that you learned about stuff in the nucleus, protons and neutrons. But this particular atom, once it's lost its only electron, looks like this, and that's all that's there is a proton. So when it's by itself, it's a hydrogen ion, and it's called a proton. And the key to this question and the next one, because you're going to have two versions, exactly the same levels of difficulty as these two, is to spot the conjugate pair that is already there, and then you have to figure out the missing molecule Y. All right. So does this molecule have the same functional groups as this one? Missing or having an extra proton? And the answer is no. I see an alcohol here and an ammonium ion here. And no, I think this species is the one that's closer to this one. And I didn't do step 0 that I told you to do in all my other videos, so I'm going to make sure I do that. K plus has no bearing on this problem, except it's there to balance the charge that this thing obtained when it lost its proton from this thing. That makes those a conjugate pair. And I'm just not happy with my anion there. It's not writing all the time. I didn't pick a pen. There. And which one of those has the extra proton? The one on the left or the one on the right? Because the one with the extra proton is the acid, and I need to place a pKa under it. And yes, that's the proton that made O- into OH. Add an H plus to an O-, you get an OH. And the pKa of a carboxylic acid, you're going to know by test day, and you're going to know it for every test until the end of organic chemistry, which is not even the end of this course. It's the next one. pKa 5 for a carboxylic acid. All right. So that means by default, these are a conjugate pair. And you're saying, how do I know if this is an acid or a base? And I got an answer for you. Acids react with bases and bases react with acids. So we've already determined this is an acid. This must be the conjugate base. Bases react with acids. The conjugate base of this. And which H comes off first to make it into its conjugate base? Are you going to pick an alcohol with a pKa of 17? If you do, then I'm going to chastise you for not knowing that lower pKa's mean stronger acids. I'm about to cross this number off, because when you have a molecule that also has a pKa of 10, the 10 is 10 million times more reactive as an acid than the 17, please ignore the 17. It has no bearing on this problem. The 10 will react before the 17. So your molecule Y, which you're going to put right here, molecule Y is the ammonium ion missing its H plus, which means it's now back to being a neutral amine, and don't change anything else. Your conjugate pairs must be different by only a proton. And there you have that. And what we want to do now is figure out the pKb's of the conjugate acids, bases, even though, you know, it's out of order. But if you look at my other videos, I always do that right as soon as I do a pKa for an acid, I go over to its conjugate base and do a pKb, because the relationship between pKa for an acid and pKb for its conjugate base is that when you add the two numbers together, you get 14. So reorganizing pKa plus pKb gives 14. To give pKb equals 14 minus pKa, you get 14 minus 5 equals 9. Similarly, over here, molecule Y is the conjugate base of this. Molecule Y has a pKb 14 minus its conjugate acid's pKa. And just like this was a much stronger acid not just like, new story. This is a much stronger acid on this side than this side. And this is a much stronger base on this side than this side. Remember, the lower the number, the stronger. Make sure you're comparing the entities that are the same. Compare bases or compare acids. And both of those things tell you you should be circling the arrow that points away from the more reactive things towards the less reactive things. This equilibrium will proceed from the left to the right to make more stable molecules. We have both a more stable acid and a more stable base. And we can do pKeq now. Let's do that in a nice color, purple. We take the acid from the left side of the equation because it's written properly. As we normally write an acid-base reaction, acid gives up a proton and becomes its conjugate base. This one gives up a proton from right to left, so the pKa is backwards. So we subtract the 10 from the 5. And KEQ is just 10 to the negative of the answer to the previous question. That is just math. There's no magic there. Whatever answer you got for pKeq, you raise 10 to the negative exponent of this answer, and you get 10 to the 5th. And I think we did all the parts. pKa values under each acid. Check, check. pKeq, did it here. Equilibrium arrow that is favored. This reaction favors the right side over the left side by a factor of 100,000. We have 100,000 more product molecules than reactant molecules. That's what that number says. And you said with an arrow, a circled arrow, that the same thing. And then pKb we did for each base. So we're going to do it at the next level and make it a little more real in the next one. Unless you have a question before we leave this page and go to the next one. We're good? Get some water here. Here we go. Now this one involves a little more thinking. What have I done here? Well, this is a tripeptide. That means a very tiny protein. In fact, it's a little too small to be called a protein, but you know, if it got bigger, it'd be a protein. And I have infinite possibilities of tripeptides. I won't run out before I retire, trust me. So you'll always have a unique tripeptide you've never seen before on any test anywhere. And you will be drawing the conjugate partner of that tripeptide. You look back at the last 8 exams, it's always been the case. And lately, I've been giving you a new acid over here and seeing if you can figure out how to use pKa's when I give them to you. So let's just start with the citric acid part. What does it mean when I give you 4 pKa's? That means we have a fully protonated citric acid. That's the one with the lowest pKa. I hope it makes sense that the number that's the lowest represents the one that has the most protons. So even if you didn't have the structure above, this is what citric acid would be in its fully protonated form, H4A. And then when it loses a proton, it becomes H3A negative. And the new pKa for the second H is 4.6. And this would be H2A2 minus. It's giving me trouble today. And it became an eraser. I'm still learning my new pen. And this is the last proton remaining. Hey, if I gave you 5 pKa's, this would represent H5A, and this would represent HA with a 4 minus. Okay, now the question is, when I go from here to here, well, it's hard to tell with all those useless potassiums. Minus, minus, minus. How many H's are missing from that one? Well, remember, K takes the place of potassium. H plus goes where there's O minus. I think there's only one left. Are you surprised that it's 18? Heck no. What functional group's that? That's an alcohol. That number I kind of knew already, didn't I? So this species has an acid. If I need that pKa, it's 18. But I don't think I do, because this species up here, there's a minus there, a minus there. This has got the extra H, doesn't it? So this is the acid. How do I know it's the acid? And over here is its conjugate base. Remember, on the previous problem, I told you to start with the pair that's already there. This is the pair that's already there. The acid has one more proton, and there it is right there. What's its pKa? Please don't tell me 3.1. Please don't tell me 4.6. This thing has 2 protons. There and there. Please don't count these protons. Those aren't the protons I'm talking about. This is H2A, 2 negative. So pKa of this species is 6.4. You were told that. Acids react with bases. This is the conjugate base of this. We need to figure out what the pKa of the green acid is. And before we do that, why don't I do the pKb of this base? How do we do pKb's of bases again? Remember, for a conjugate pair, pKa and pKb add to 14. 14 minus 6.4, 7.6. Show your work, because I'll see as many students give me 6.6 by mistakes as I'll see students give me 8.6. No calculators. And if you set it up right and give me the wrong answer here, you're at least getting something. Give me only a wrong answer, you're getting nothing. Okay. Base, acid. Oh, we got some work to do. We got clues here. Got some clues. Do you know where you also have clues? For the same molecule? I think. I can't remember 100% because COVID changed our lives a lot. I'm just going to go back to the test and see if on part 1 there's more clues. And there might not be because we had to shorten things. And it looks like, no, I stopped doing that. No more clues, part 1. So you won't have another clue. You should have everything you need here. This says pKa1 is 2.2 for the carboxylic acid that's associated with TEAR in the molecule. Here's the name, ASP H-cis, which stands for homocysteine if you're curious, but that's not important. It's the middle part of the molecule. That's all you need to know. And TEAR is over here. Where's the thing that looks most like a carboxylic acid over here? It's right here. What this means is when it has its proton, the pKa is 2.2. It currently does not have the proton. So we are not using 2.2. It is missing. It is not relevant in this question. pKa2 is 4.9 with no clues. Oh. pKa3 is a thiol. Okay, I never taught this yet, but if you've been looking at exams, it shows up on at least half of them, and I just assume that you've gone through exams, and you should know a thiol is the same as an alcohol, except the O has been replaced with a sulfur. Learn that now. So this is the S minus of the thiol. This is the conjugate base of the thiol. So I'm not even using 8.9. And if 8.9 is missing, it's missing. Look, there's no H there. Then 4.9 was missing before that one. I suspect the 4.9 was this because that's close to the number for a carboxylic acid. And that looks a heck of a lot like the conjugate base of a carboxylic acid. So we could I expect you to be able to figure out the 4.9 should be there, but you don't even need to for this problem. Let's see if the 9.8's there. What do we got? We got a phenol. It says the phenol is 10.1. We know what phen is now, or maybe we haven't read chapter 5 yet. Phenyl, this is chapter 5 preview. It's coming up on your test anyway. Phenyl is a group, which means it's stuck to something and it has a benzene structure attached. It's right there. Phenol is a molecule. It has an OL, alcohol, attached to a phenyl. The name says it, doesn't it? If that's a phenyl and this a phenol. So this portion is a phenol. That's the exact same thing as I just drew. That's 10.1, but it's not relevant in this question because the 9.8 is, what is it close to? Didn't we learn a 10 on our pKa table? Yes, please. That pKa table has to be up here very soon. For every test in Chem 241 and 242 from now on. Ask my 242 students, do those pKa's ever go away? He said, no, they're on every test. The 9.8 is for the ammonium ion right here, and that is present. It is the relevant pKa for this problem. How do I know it is relevant and not the 10.1? I know that's a question on many of your minds. The numbers are close, but which one is lower? Because lower means more reactive. More reactive means reacts before. So the 9.8 will react before the 10.1. Show me you know that by drawing molecule Z with only the H plus missing. And sadly, during COVID, we got to do the whole molecule. We can't circle it on the exam like we used to. So that's okay. We practice drawing molecules. I'm going to copy the whole thing. I'm going to cross the spectators off. Yeah, we got another one here. There we go. So the molecule Z, here's Z. I'm just going to carefully copy from the top. O2C goes to C, comes down to NH2. That's the thing that lost the proton. That's where the money is. Showing me you know that. And H goes to C, goes to CCC. Oh, I don't know why it's doing that. Okay, S minus didn't change. Please, no other changes. In acid-base reactions, only one proton moves.
Professor?
If you have multiple things happening, you're going to lose multiple points. Yes, sir.
So you see how the NH3 group has the plus on top of it?
Yep.
Right?
That's an ammonia.
Would you be able to like tell that that's what's going to have to change, but you wouldn't have the pKa from, right?
No, I had a choice between this one that has a proton and this one. I had to use the clues to figure out which of those two were the ones that had to react.
Oh, okay.
I had to find out what H's were there. First of all, I had to take it from the beginning and realize I need the lowest pKa on this molecule.
Yeah.
If this was a base, I'd have to find the lowest pKb on this molecule. This isn't a base because this is the conjugate base of that. The question is now, what is the acid that's going to react first to go from here to here? And of the remaining protons, a 9.8 reacts ahead of a 10.1.
Okay, so it's basically because it's more reactive. It's not like,
Yes, lower number means more reactive.
okay, so you'd pick the one that's more reactive than the, okay.
Mhm. My pen is out to get me. And I don't want to change this group either. I drew it a little different, but it's not really. Put a big fat dot there. There we go. And I didn't, oh, careful. Don't get careless here. All right. Was the only change going from NH3 plus to NH2? And the answer is yes, because I copied that to carbonyl to NH, amide, S minus, back up to carbonyl, amide, C up to CH2 to a phenyl with an OH as far away as possible. There you go. Okay, we're in business. And what is the pKb of my base since we're here? We picked the right pKa, was the 9.8. So what's the pKb for its conjugate base? 14 minus what number? Well, what was the pKa you took off to get here? It was a 9.8. And remember, if that number was 10, we'd be at 4. We're 0.2 below 10. So 0.2 below 4. And no, it's not. It's 4.8. The difference is greater than 4 because we're lower than 10. I don't know. Sometimes my explanation of math is like from a different planet. There. Hey, I always verify. 0.8 plus 0.2 gives a 0. Carry the 1. 13 becomes 14. Good. All right. And that's pKb. We've got a pKeq. The acid on the left was 9.8. The acid on the right is 6.4. It's always left minus right. Don't change reality. 8 minus 4 is 4. 9 minus 6 is 3. KEQ is now 10 to the negative 3.4, which means this equilibrium is going to stay to the left. And hey, you don't need to do the math to do that. Which acid's more stable, a 6.4 or a 9.8? The answer is the higher numbers, more stable. More stable means less reactive. Higher numbers are less reactive. Lower numbers for pKa are more reactive. And I think we finished the question. We better save that. Valuable work here. It's getting dark here too. All right. So we got that one. What you want to do next?
Let me just find it because I don't know where it is.
Oh, why don't we just come back after a stop, and then you'll probably have
Okay,
it
yeah,
by
that
then.
sounds great.
Sound good? All
Yeah.
right. I'll see you in about, let's see this. I don't know how long that took, but maybe 6 minutes.